next example here is also based on normal extensions. And it says that any extension field which has a degree of 2, that means you have an extension E over F, and the degree of this extension field over the field F, that is given to be 2, then that extension field is a normal extension. So this is the example. Let us see how this works. So for that, because the degree given is to be 2, that means this is a finite extension. If this is a finite extension, it implies it is also an algebraic extension. If this is an algebraic extension, so we assume some element alpha which is present in it. So we assume that this alpha is present in E, but this alpha is not present in E. Because this is the larger set, it may contain some element which are not present here. So that is why we assume that particular element which is present in E, but that is not present in F. Now because it is a finite extension, this is also an algebraic extension. So corresponding to this, each element here would be algebraic element. If this is an algebraic element, that means we have some polynomial px which is the minimal polynomial of that element over F. So let us assume that between this E and F we have one other extension field naming to be F of alpha, where alpha had been adjoined to this one. So now what would be the degree of this field over this field? Here alpha belongs to this element extension field F of alpha. So that means corresponding to this element here we have minimal polynomial p of x in capital F of x, such that this is the minimal polynomial, and the degree of this F of alpha over F, what would be that? It would be the degree of this polynomial p of x. But we as of now do not know what is this degree. What is the degree of this polynomial p of x? However, what we know is the degree of this E over F, that is equal to 2. This is given in the question, that the degree of this polynomial over F is given to be 2. So now we have this trio of extensions. So E over F degree, that is given to be 2, but we can also write the degree of E over F as the degree of E over F alpha and the degree of F alpha over F. So like this, and this is equal to 2. Now because they cannot be equal, because we have assumed the construction in such a way that this alpha does not belong to capital F. That means they both cannot be equal because alpha is here. So that means the degree of this one cannot be 0. This is not equal to 1. If the degree is 1, they both have to be equal, but here they are not equal. So that means this degree cannot be 2 and this is 2. The product is 2. That means one has to be 1, one has to be 2. So this degree would be 2 and this degree would be 1. So if this degree is 2, that is what we have written. This degree is 2 and this degree is 1. This degree 2 implies that this degree was what? The degree of px, the minimal polynomial px. So that means the degree of this minimal polynomial px is 2. That means px has 2 roots. And another information that we got from here is that the degree of E over F alpha is equal to 1. If the degree is equal to 1, that means they are nothing but the same extension fields. So from here we got this information, and from here we got this information that the minimal polynomial px has 2 roots. Now as one root of this px is present in E, one root of px is, px has one root as alpha, which we have assumed in E in the very starting of this proof, right? Alpha was present in E and alpha is also the root of this polynomial because this is the minimal polynomial of alpha. So other root of px must also be present in E, because E is nothing but f of alpha, and because alpha is present in f of alpha, so all the linear combinations of alpha are also present in this f alpha. So that means the other root for this polynomial px is also present in E. Now it has two roots and all of them are present in E, so that means we say that the given polynomial px that splits into linear factors in E. And if the polynomial splits into linear factors in E, that means E becomes the splitting field of the polynomial px belonging to f of x. Thus E becomes the normal extension, and this was what we intended to prove. So I hope this one is clear to you.